Hello and welcome to my video on an expanded pattern of phi, or the golden ratio. I'm going to be showing how this pattern is manifested in a series of parabolas using a great freeware tool called GeoGebra, and I think the visuals will make the pattern really stand out. I even managed a bit of animation. I'm also using Excel spreadsheets, which are great for making small changes to a formula and seeing a wide range of results. As a brief outline, and if you like to use the YouTube timestamps, Chapter 1 will show the basics of this expanded phi pattern, for want of a better term, in the parabolas and their respective quadratic equations. In Chapter 2, I'll be adding right triangles to the series of parabolas and showing how the ratios of their sides are connected in a way that I think you'll find pretty unexpected. Chapter 3 will show how the golden ratio and the silver ratio are both essential parts of the parabola, described by x squared minus x minus 1, which is your standard parabola for getting phi. And in Chapter 4, we'll look at how the Fibonacci series enters into all this. The means of using the Fibonacci numbers to get this expanded phi pattern is similar to, but not the same as, the way it's used to get the silver and other metal ratios. What we're looking at on the screen is a parabola based on the quadratic formula f of x equals x squared minus x. Now, f of x is another way of just saying y, and for this point right here, y is 1. So for that point there, 1 is equal to x squared minus x, and if we add x to both sides, we get positive x plus 1 equals x squared. And what number, if you square it, is the same as adding 1 to itself? Well, that number is phi, 1.618, and some of you are familiar with that and some of you are not, but we're going to get more into the details. So at this point, y is equal to 1. Now, if we were to lower this parabola by 1, or subtract 1, we would get x squared minus x minus 1. Now, this is the parabola where you usually find phi, and this is based on the quadratic formula. You can see on the left is the quadratic equation, x squared plus x plus c equals 0, and on the right is where you plug in the coefficients. So I've done a little bit of Excel work here, and you can see that if you have 1x squared minus x minus 1, the number that is under the square root sign, or the radix, is 5. Phi is equal to 1 plus the square root of 5 over 2. We're going to be looking at the positive numbers only in this video. Phi is an irrational number, and the idea of a number that if you square it, it's the same as itself plus 1 is pretty cool. But the idea of an irrational number being, if you square it, being the same as itself plus an integer is the theme of this video. So if you stop and think about it, what number, if you square it, is the same as itself plus 2? And we know that that number would be 2. So as before, in this case, y is equal to 2. And so if we add x to both sides, we get x plus 2 equals x squared. Of course, same concept. And if we plug that into our quadratic formula, we're going to see that minus 2 is going to put 9 under the radix, which of course makes sense because 1 plus 3 over 2 is going to give you 2. Now, if we go the other way, and we go down to 1, you can see that if c is equal to 0, then the number in the radix is going to be 1. And of course, 1 plus 1 over 2 is going to give you 1. So what we notice here is that the number in the radix is increasing by 4 each time. And so that would seem to indicate that the next one up is going to be 1 plus the square root of 13 over 2, we can see that that's correct. And we can also see that the x point is going to be 2.302. And if we square it, it's going to be 5.302, which is the same as x plus 3. And this pattern is going to continue on our x squared minus x parabola. So this will be 1 plus the square root of 17, 1 plus the square root of 21 over 2, and of course 1 plus the square root of 25, which is 1 plus 5, which is 6 over 2, which is 3. And if you square that, it's 9, and 3 plus 6 is equal to 9. So this is the expanded phi pattern, if you will. And it also applies is that the corresponding parabolas that are described by the quadratic equations x squared minus x minus 2 minus 3 minus 4 are all going to correspond to these same points. So this pattern is going to continue all along the x-axis if we drop these down by 1, by 2, by 3, etc. And I've got a little bit of a neater animation to show what that looks like. It just looks cool, a little bit of eye candy to look at while we're moving to the next step. So you can see the same points here on the x squared minus x parabola. And if we drag it down, you can see that all the points come down onto the x-axis. And if we raise each one, again, if we take x squared minus x minus 1 and raise it up by 1, and x squared minus x minus 2 and raise it up by 2, you're going to see that they all obviously fit very nicely onto the x squared minus x parabola. And let's do that one more time just for the sake of seeing it. All these points come down here and then go back up. We're going to look at the relationship between some triangles that are associated with these different points. So I've created here 3 triangles. The vertex at 0.5, negative 0.25, has a length of 1.25 going up to this point at 1. I'm going to call that B of the first triangle. This line here, this side here, is phi minus 0.5, which is 1.118. And this is the C of the first triangle. Now 1.118, 0.33, etc. If you square it, you get 1.25. And if you take a squared plus b squared, you get, and take the square root of it, you get 1.677, which is C, which makes sense. That's the Pythagorean theorem. So for the second triangle, the length is going to be from negative 0.25 up to 2. So the length there will be 2.25, and that will be our, let's say, B sub 1. And A sub 1, the length is 1.5. Now, of course, 1.5 squared is 2.25, and then the square root of A squared plus B squared is going to give us C sub 1, and that is 2.704. And the third triangle is going to have B2 with a length of 3.25 and A2, which is the square root of 3.25, and then C2 gets us 3.716. So if we take C of the first triangle, 1.677, and divide it by A, 1.118, we get 1.5. And that's our A1. If we take C of the second triangle, 2.704 over A of the second triangle, we get 1.802, which is A of the third triangle. So that brings up a very important point, because if the Pythagorean theorem says that C equals the square root of A squared plus B squared, then how is C over A anything that you can establish a pattern with? Because as you can see, there's no direct relationship between C and A. You can't have C unless you have A squared plus B squared and you have the square root sign. And the problem here is this is an addition operation, and square roots are not distributive across addition. So again, the dilemma that we're faced here with is, how is C over A? First of all, how is it a thing in the first place? And second of all, how is it predicting another triangle entirely? So we're going to find out how this occurs, and the main point here is going to be that A squared is equal to B. So let's take a look at this for a moment. Let's say that C is equal to the square root of A squared squared, which is A to the fourth, plus A squared. Well, that still doesn't tell us too much, because again, we're adding. And square roots, again, are not distributive across addition. This doesn't mean anything. You don't get anything by adding these two. What if we say, since we know that A squared equals B, C is equal to the square root of B squared plus B, which is saying the same thing. Let's say that we've got a triangle, and A is 2 and B is 2 squared, and we know that C is going to be the square root of 20. So A squared is going to be 4 in this case, and B squared is going to be 16. And what happens when we're squaring B and adding B? And I'm going to make this visual just for the folks out there who maybe don't deal with this on any kind of regular basis. So if we're squaring 4, we're taking 4 4s. And then we're adding 4. So we're adding a 4. Now what have we done? We've got now 5 4s. So we've got 4 times 5. If B were equal to 5 and we squared it, we'd have 25, which again is 5 5s. And we add a 5, we're getting 6 5s. And so what we've done here is essentially we're multiplying the square root of B times the square root of B plus 1. B squared plus B. The same thing. So what we've done here is we've made this a multiplication operation, and square roots are distributive across multiplication. So the square root of B times the square root of B plus 1. So for our example, the square root of 4 times the square root of 5 is equal to the square root of 20. And the reason why C over A is equal to A1 is because B, each subsequent B is B plus 1. So the square root of B times the square root of B1 is going to get you C. And the square root of B is A, and the square root of B1 is A1. And so A times A1 is equal to C. And A1 times A2 is equal to C1. And A2 times A3 is equal to C2, etc. And this is why the C over A ratio is always equal to the A of the next triangle up. These are all related to the distances of these phi, expanded phi pattern numbers that we've been looking at. Okay, so for this part, I'd like to place the focus up here at the coordinates of point A. And we can move this in this GeoGebra application, and you can see the coordinates move. You can see that all the points under the X coordinate here, X is greater than Y. When you get to 1, and you start going up, x is still greater than y, and it's going to be greater than y until you hit a kind of an equilibrium, and on the parabola x squared minus x, that equilibrium point, for want of a better term, is 2, 2. And you can see when you start going above that, now y starts exceeding x. So for x squared minus x, this, I'll call it equilibrium point, is at 2. But as we know, the x-intercept for x squared minus x minus 1 is phi. It's x equals phi and y equals 0. Now we're going to see that this is the golden ratio. The silver ratio also appears on this same parabola, and it's an essential part of the parabola. And again, we're going to put a point on here, and we're going to move it like we did on the one above. And you can see that x is greater than y up to a certain point, and it's a little hard to nail down. I'm going to make it easier. It's going to be the point where x equals y, and we're going to just put a line from 0 to 2 on the first parabola, and then we're going to do the intersection, that line, with the next parabola. And you can see that the points there are 2.41421 and 2.41421, which happens to be 1 plus the square root of 2, and that is the silver ratio. So the silver ratio and the golden ratio show up on the same exact parabola. We can also see that the angle of this line is 45 degrees. So the next equilibrium point up is at 2.73205. And if we take square root of 3 and add 1, we get 2.732, and this is the 1 plus the square root of 3. 1, 2, 3. And that pattern does continue. The final thing I want to look at is the Fibonacci numbers and how the pattern of numbers that we've been looking at are related to the Fibonacci numbers. So right now we know the basic pattern of the Fibonacci numbers. We've got 0, we add 1, we get 1, we add 1, we get 2. 2 plus 3 is 5, 5 plus 3 is 8, etc. And if we take the ratio of each number to the previous number, we get to phi. Now, over on the left, this is 1 plus the square root of this over 2. So that gets you phi. If you remember our formula, if we've got x squared minus x minus 1, then it'll be 1 plus the square root of 5 over 2, which gets us 5. If we take a squared minus x minus 2, we're going to get 1 plus the square root of 9, which, if you square it, gets you 4. And if we take x squared minus x minus 3, we'll get 1 plus the square root of 13, which, if you square it, is the same as itself, plus 3. And those are the numbers that we have here in this column. So if we take the ordinary Fibonacci numbers and we just add them up, the ratio that we get is going to be phi. So if you remember the original parabola, we've got phi is x is phi and y is 1, x is 2, y is 2, x is 3, 2.303, y is 3, and y keeps increasing by 1 each time. So if we take the Fibonacci numbers and each time that we add numbers together, we multiply them by 1, which I know is counterintuitive because why would you do that? But it certainly doesn't hurt anything. Everything is multiplied by 1. By default, you get phi. Now, if we take those numbers and we multiply them by 2, then the ratio converges on 2. These numbers, of course, are not 2. They are converging on 2. I just don't have it set to expand the decimal points out forever. So again, all I'm doing here is taking the numbers that are added up. So each time we add the numbers together, I'm going to take the new number and multiply it by this number in this square. So I'm multiplying this number by 1 and this number by 1, which gets you 8. And at this point, you don't see any changes. So what we're doing each time is we're taking the number in this second column, multiplying it by 2, and moving it to the first column. And then we're taking the number that they add up to and making that the next second column. So 2 plus 1 equals 3. 3 goes here. 1 times 2, 2 goes here. 2 plus 3 equals 5. We move the 5 down to here. We multiply 3 by 2, and we move it to here. 6 plus 5 is 11. Move the 11 down here. 5 times 2 is 10, and so on. And we can see that by doing that, we get numbers that converge on 2. Now, if we do this for 3, again, this number keeps moving down to be the second column, and then we're taking this number and multiplying it by 3. This number multiplying by 3, and the ratio of each number above the next one is 2.302, which is the next in our series. And if we do 4, we get 2.56, and that's the next number in the series. And then, of course, if we do 6, it's going to converge on 3. Now, the silver and other metal ratios are similarly obtained with the Fibonacci numbers, but slightly differently. So we're taking the Fibonacci numbers again, and you can see here you have the Fibonacci number series. And the ratio is 5. For the silver ratio, we make this 2. And now what we're doing is we're taking the third column, multiplying it by 2, and then we get 4. And 1 plus 4 is 5, and we multiply that by 2, and we get 10. And this number is equal to 2 back. There are videos of this procedure that are much better than this, but it's a similar concept to what we're doing. We're just doing our multiplication at a different stage. Now, the metal ratios do have some correlation with these numbers, but that's too much for this video, so I'm going to save that for a future video. There's a lot more here as an introductory video. Obviously, I've been trying to fit an awful lot of information into one video, but there is more to be seen here. Thank you very much for your attention. If you like the video, please hit like and comment and subscribe if you would like to see more. Thank you very much.